Hi guys, my name is Brianna Rapp. I play soccer here at Mount. I'm a biomedical engineering major, and I am a double minor in exercise science and German. So as you can tell, I am very busy with my coursework and soccer, and I drink coffee every single day, which really brought me up to the discussion of the chemistry behind coffee. Why coffee? Well, 64% of Americans above the age 18 drink coffee every day in 2019, according to the National Coffee Association. And men on average, drink more coffee than women, but women spend a lot more money on coffee than men. And 60 and above actually drink the most coffee. It's also America's #1 choice of beverage. Per capita, 88.8 gallons are drank every single day per American, compared to its counterpart like carbonates, which would be soda or pop, which is 39.5, and even bottled water, which is 33.5 gallons. So I will be discussing the science behind how coffee is brewed, what compounds are in coffee, and the analytical techniques of determining those compounds, and how the coffee affects your body. So the science behind how coffee is brewed. There's a lot of things that go behind brewing the perfect cup of coffee, but more specifically, the temperature of water, quality of water, particle size distribution, the amount of CO2 in the coffee bean, and water to bean ratio, and it's something called the Maillard reaction, which I will be discussing in more detail later on. So the importance of water. So you want the temperatures of water to be high because it increases the efficiency of extract of the caffeine, but you do not want them to be too high because then it can produce a burning taste. And so cold brew takes a lot longer for it to brew because actually if you look here, as temperature decreases, the longer and the efficiency of the extract will take longer. And you want the pH of water to be around 7 because less than 7 can create a soft tasting water, so it would be sour tasting, and more than 7 will actually create a hard water, which would be chalky tasting. So the coffee bean is very important. You want small and consistent grounds of coffee, and you want coffee with high levels of CO2, because as CO2 increases, so does the freshness. As you can see here, within the day, so I'd be looking around the first day, it's at a 40% concentration. But it exponentially goes down within the next 10 days, so the freshness of coffee goes down quite a bit. And it kind of levels off after day 20 and day 40. So the Maillard reaction, and this is basically an application of heat to the coffee, which can create new aromas and new flavors, and this is known as browning. And actually a lot of other foods go through browning. It's like cooking, and it would be like roasting a turkey or roasting marshmallows. And what compounds are in coffee, and the analytical process used to determine those compounds. So here are a few examples, but more specifically I'll be talking about purine alkaloids, the aromas contributing to smell and taste, and chromatography, which helps determine what compounds are in coffee. So here are a few examples of compounds in coffee, but more specifically I'll be talking about caffeine and chlorogenic acid. So purine alkaloids. So there's theophylline, theobromine, and caffeine. And these are all structurally very similar to adenine and guanine. And those are the active components within energy drinks that gives it such a strong effect. And these are basically just the unmodified version of these. And compounds contributing to taste. So chlorogenic acid after roasting becomes chlorogenic acid lactose. It originally is a sour tasting substance, but then turns into a bitter tasting after roasting. Compounds contributing to aromas. So there's beta-dasconine, which contributes to honey or fruity-like, and there's 2-fluoroethyl, which is the roast or the coffee smell, and same with 3-thiol-2-butane 1-thiol, which is the roast smell. And the analytical process to determine coffee is called chromatography. And there's a lot of different uses, but it basically sorts out different molecules based on their characteristics and properties. And it's useful when determining what molecules are in a certain compound that is just unknown. In stages, so I'll be discussing stationary, and that's when the substance goes through a porous matter but stays stationary and just doesn't move. And then mobile is when a substance is put through a porous matter and it becomes mobile, so it will sort through really easily. different types of chromatography. So there's affinity. And affinity uses so first you have a compound of a mixture, and it has active sites. As you can see here, the target active sites so these will go into here, and the rest will be sorted out like this, so it can easily help separate those two, and then afterwards you can actually separate them to get for the pure substance. And then the anion and cation exchange. So first, this will be the cation exchange, and it's when the positive cations are on the outside, so it uses the law of attraction, so positive anions will sort through, but the negative anions will actually stay to the side, allowing for the separation. And cations go through the same thing, except it would be a negatively charged here, so negatively charged would go through, and then the positive charge would stay. And then column. So you insert the sample here, and it's sorted through, and you typically hear, or this would be the stationary phase, so a lot of things will just stay still before it gets sorted through, and there would be a porous matter such as silicon beads that will help determine. And I actually did this lab, and here it'll become little strands. That's really easy to identify the shapes and the size. And then flash. So flash is exactly like column, except it uses pressurized gas to make the process a lot faster. And then gas. So you insert the substance right here, and it's vaporized in this oven. And depending on how big the molecules is, and it also uses heliums to allow a mobile gas, so like helium, to allow the molecules to stay afloat. And depending on how small the molecules are, it'll sort out first, and it will become detected by a computer and data analysis, while the bigger ones will be a lot slower and come out last. And then gel filtration or size exclusion. So these are used with a lot of proteins or DNA strands. And so basically there will be porous beads right here, and it'll be more of a thicker substance that it'll sort through. And a lot of times they'll illuminate what strands they want to sort through, so you can see it a lot easier. And it'll become like a band almost, just slowly going through, while all the other molecules, because they're a lot smaller, will go through a lot faster. So it'll give out the pure gene. So different types of chromatography continued. So there's something called high performance liquid chromatography. And that is like chromatography, except it occurs a lot faster. It's like column chromatography, and it occurs a lot faster, and a computer is actually analyzing when the molecules come out. The hydrophobic interactions. So there would be hydrophobic interactions right here. So the hydrophobic ions will actually be on the side. So as they go down, it uses the law of attraction again. So hydrophilic molecules will actually stick to these ends, and then hydrophobic ones will go through. And then ion exchange is exactly like cation and ion exchange that I discussed in the previous slide, except this is more of the general term for it. And then the liquid, so it's sorted through here, and it's like the column, except it's on the side, and it just basically sorts out the size, but it doesn't use the size or the volume, it just uses the mass. So it'd be how heavy it is to sort through. And then reverse phase, so this is a solvent or paper, and they dump the paper into here, and depending on the size, so smaller molecules would be up here and bigger ones would be down here. You can actually determine what size they are of how far they are from the origin. So reverse. So they basically do the same thing. They separate the molecules using hydrophobic interactions, and it's almost like the same thing, except this one would be used with a lot more organic compounds and proteins. So thin layer is kind of like gel electrophoresis, but instead of using DNA strands and charge, they use the substrates, which would be inserted through these docks right here, and they use gravity to sort throughout the size. And this would be like buffer solution, so it can travel easier. And so chromatography used in coffee. So they use high performance chromatography, gas chromatography, and ion chromatography. So high performance chromatography is like column chromatography, except it occurs at a lot faster rates, and it uses a computer to determine what compounds are in that mixture. And the higher affinity molecules will move slower, and lower affinities will move faster. So those will be the first ones to show up. And as you can see, like right here, this would be the time it increases as it goes because of the affinity. And then high performance liquid chromatography helped identify chlorogenic acid, caffeine, trigonylene, and nicotinic acid, which would be right here, the compounds. And so gas chromatography. So they insert the mixture right here. It would be vaporized in this oven, and it sorts the molecules based on how fast they move. And it actually uses a mobile gas such as helium to help keep them afloat, and the smaller molecules would be sorted out faster because there would be a lot more movement. And it uses a computer analyst to determine when those molecules came out compared to the time. So gas chromatography didn't really help determine anything specific, but it did help determine like large groups like carboxyl acid, trigonylene, derived dibutane. And then ion chromatography. So this is similar to gas chromatography when determining what compounds are in there, but it more determined it was a lot more generalized. So it separates the molecules based on charge, and it uses the law of attraction to separate them. So positively charged ions will actually repel, so they would go down, and negative ones would actually stick, and vice versa. And this helped sort out carboxyl acids through the column. So how coffee affects your body. So within this one, I'll be discussing mental alertness, antioxidants, and the long-term and short-term benefits and risks. So benefits of drinking coffee. Short-term, it improves cognitive awareness, and actually can improve your athletic performance, and it's rich in antioxidants. And if you don't know what antioxidants are, they basically help fight free radicals in the body, which contribute to cancer. In long term, it decreases your risk of Alzheimer's. Negatives of drinking coffee. Well, it increases your risk of type 2 diabetes and liver disease. But the type 2 diabetes can be attributed to the fact that a lot of people put creamer and sugar into their coffee, which already has a direct causation to diabetes. And why does this matter? Well, there's huge economies built around creating the perfect cup of coffee, and there's a huge import system. And practically everyone in this world drinks coffee. And here are my references.